Welcome to the 7th Tartarus Devlog. In this video, I'll discuss callback functions and give an in-depth overview of Tartarus's new callback component and callback system. Along the way, we'll review relevant code concepts and actually peer inside the Tartarus engine to see how these new features are implemented. Lastly, I'll demonstrate the new callback functionality in a couple nifty ways. In the 6th Tartarus devlog, which I released just a few months ago, almost 3 years ago. Goodness gracious, I need to start releasing content more regularly. We looked at text rendering. This video will focus on a completely different topic, callback functions. To get where we're headed, let's revisit some of the concepts and visuals we discussed in Affliction Devlog 0. Here we have an entity which is defined by its components, and individual systems operate and/or depend on some combination of these components. Side note, I'd need to say the phrase operate and/or depend on quite a bit throughout this video, so instead I'll abbreviate it as just operate on, and you'll know to expand the term. We could imagine that this is, say, the Tartarbus entity. The entity might include the transform, health, attributes, and properties components. In this case, the motion system operates on the transform component, the health system operates on the health component, and so on. And we extend this to whatever number of entities, components, and systems we desire. However, what's not trivial in an entity component system architecture, or ECS, is interaction between components. And I don't mean it in the sense that a system operates on multiple components simultaneously, like with this hypothetical damage system. I mean an interaction in which one component can have a direct but arbitrary impact on any other component belonging to the entity without requiring the design of an additional system with all the necessary but annoying boilerplate code. Back in the generic case, I'm trying to describe an interaction that looks something like this. Let's imagine these components are actually the highlight and attributes components. The attributes component allows it to be rendered, and when an entity gets picked, check out Engine Devlog 4 for more details, it gets highlighted. As a real example, suppose we want the entity's color to change anytime it's highlighted. How would we implement such behavior? It's actually significantly more challenging than what you might think to do this in a flexible, scalable manner, at least in C++. For instance, we could design the picking system to operate on the attributes component or the rendering system to operate on the highlight component. But that means anytime we want to introduce a new component-component interaction, we'd have to modify the underlying systems to operate on additional components. Those lists of components could grow quite lengthy. And besides, picking technically doesn't have anything to do with an entity's visual attributes. Likewise, rendering technically doesn't directly depend on picking or highlighting. Another approach, like I mentioned a minute ago, is to create a system that operates on both components simultaneously. Something like this change color system. However, this is yet again an inflexible solution, because anytime we want to establish a new component-component interaction, we have to implement yet another system. What we really need is some type of functionality that will allow us to define an arbitrary number of interactions between an arbitrary number of components. This functionality would keep the other systems completely isolated, but also help us avoid needing to define and explicitly write out a new system for each interaction. That segues us to the focus of this video, callback functions. But don't worry, we'll revisit this diagram in a little while. For me, callback functions have often held an unnecessarily mysterious aura to them. They sound special and arcane, but actually, a callback function is just an ordinary function that gets called by another parent function. Here's a contrived example using Python code, which is much easier to use for demonstration due to its weak typing. I won't go into detail on everything the code does, but if you know programming fundamentals, you should be able to follow along without much trouble, regardless if you have any experience in Python. Obviously, you're welcome to pause if you need more time to parse the code. Suppose we want to cast a list of numbers to integers and print the resulting list to the terminal. In the top left, we define a function called casti in print that takes a list and, in line 2, iterates over each element in the list to cast it as an integer. Then prints the function name and the result in line 3. Then, in the top right, we create a list called inputs that's comprised of multiple sublists of floats. And inside the for loop, starting on line 7, we execute the function on each sublist. In the terminal, we see something similar to what's shown in the bottom right. Each sublist with its values casted as integers. But now, there on line 2 in the top right, suppose we change the first input sublist to integers, and suppose we want to cast these as floats instead. So, we define another function in the top left starting on line 5, cast f and print. On the right, we modify our main script to check the type of the first value of each sublist and then execute the appropriate function. We cast ints to floats and floats to ints. Our terminal shows the resulting outputs, casted as we expect. But let's keep going. Now, suppose we change up our inputs list again and start including string values, like the word for in the top right on line 3. We implement a function in the top left starting on line 9 that casts values to string and prints the list. We add an additional case to our main script for loop there on the right, and we see the corresponding output in the bottom right. Okay. We can still make sense of this, but I think we'd probably agree that the for loop is on the verge of being out of control with all its conditions. There's a lot to digest here with this borderline spaghetti code, and it seems like adding another case would start to make things painful. Instead, let's look at a callback-based solution. Here's all the previous code refactored, so let's step through it, starting with the main script. We see our inputs in the top right haven't changed from before. We still have integers, strings, and floats. But now we have this object called mapping starting on line 7, a dictionary in Python, or equivalently, a map in C++, that maps key value pairs. More specifically, the mapping dictionary maps types to functions, and we'll come back to that in a second. Down on lines 13 and 14, we're still iterating over each sublist in the inputs list, but now we're just calling a single cast and print function. Down below, we can see our outputs are the same as before. Everything is so much cleaner and, as we'll see, more flexible. So what changed? Looking at our definitions in the top left, we see that we've converted all our castX and print functions to just castX. We have casti, castf, and cast_s. These functions are only returning casted values and nothing more. However, starting on line 10, we have a new function, cast and print. This function receives a list of values in a variable, assumed to be a dictionary that maps a type to a function. On line 11, the dictionary is used to look up the appropriate function given the type of the list's first value, and that function is assigned to the variable callback. On line 12, the callback variable, which stores a function, is applied to the list of values and stores the returned casted values into the output variable. Lastly, in line 13, the function prints the output variable. What we've done here is used a dictionary, the mapping variable, to specify which function to use for a given type. Then the responsibility lies with the cast and print function to execute the appropriate so-called callback function. Notice the ease with which we can switch the mapping and thereby change the behavior of the for loop. Now we can go on to add even more functions and behaviors, like the square I function in the top left starting on line 10. This function casts each value as an integer and then squares it. Trivially, in the top right, we can modify the mapping on lines 8 and 9 to use the square I function instead of the castX functions, and we see the result in the bottom right is what we expect. Hopefully, the advantage of this approach is evident. The output behavior depends on provided function definitions rather than massive if-else blocks. Sounds great, right? Well, the challenge is to implement this in C++, which has a very strong typing system. We can't pass around functions like we do in Python, at least not as easily. We'll have to work for it, and that's what we're going to look at throughout most of the rest of this video, implementing generic callback functionality in C++. To set expectations, I'm not promising to show every last detail of logic that goes into it, but just the important parts. So, if you're interested in exploring this further, you might have to do a bit more digging, but what I show should provide a good starting point. I should also mention, I've never really tried to explain C++ code in words before, so this is probably going to be a bit clunky, and maybe even incorrect. Since I'm bound to make a few mistakes, please leave a comment if I say something misleading or wrong. Alright, so here's what we're targeting. an entity that includes a highlight component, an attributes component, and a new callback component inside which we're able to store an arbitrary function. We'll also need a picking system that highlights an entity with a color when clicked, a rendering system that displays the entity's attributes, and a callback system that uses the callback component's function to apply the highlight color to the entity. That looks something like this. The callback function is some to-be-defined operation called changeColor. It accepts the highlight color value and applies that to the attribute's color value. In pseudo C++ code, this is the logical behavior we're seeking. When an entity is clicked, it's highlighted. If an entity is highlighted, its color is changed to the appropriate highlight color. Let's step through the relevant code for each of these items and see how they work. Here's the actual callback function we're going to use to modify the entity's vertex data, changeColor. In line 1, we see the function doesn't return anything, but instead operates on a reference to the entity's highlight and render mesh components, the latter of which is what stores its attributes like color and texture. On line 3, a function is called that sets the render mesh's display color to the specified color, but its details aren't important here. This is now the callback function we want to pass around. Pretty easy so far, right? Well, your arrogance betrays you. It gets bad. Here's the code we use to implement the callback component. Up top, we import the standard library's functional module so that we can use standard function later on, which I'll describe in a moment. First, we create a templated structure called callback with both a type named t and a parameter pack called args. We can see what these template parameters do in line 5. They allow us to define a member variable, in this case a standard function, that accepts the parameter pack as arguments and returns type t. The standard function is C++'s way of storing a function as an object that can be assigned to variables, like you would with an integer, string, and so on. In other words, up through line 5, we have a struct that can hold an arbitrary function, that can receive an arbitrary number of arguments of arbitrary type, and that function returns an arbitrary type. Simple, right? I'm kidding. Then, in lines 6 through 8, we overload the parentheses operator so that we can call the struct just like a plain old function, and it'll automatically call the contained standard function. This is just a cleaner way of calling the function member variable. We can just call callback on a set of arguments instead of needing to explicitly call callback.function. Down below, we define an initializing function that allows us to easily instantiate a callback object. Using template parameters with the same names in line 12, t and args, we define an init callback function on line 13. That function accepts a standard function with the same signature as what the callback struct expects. The standard function receives a parameter pack called args and returns type t. On line 15, we instantiate a new callback object. On line 16, we assign the past standard function to the new callback object's function member variable. Then, we spit out that initialized callback object on line 17. This is our callback component. Before moving on, let me provide some words of encouragement. If some or even most of this looks like gibberish to you, even if you've been working with C++ for a few years, don't fear. It took me a very long time to get somewhat comfortable with C++ templates, and to be honest, I feel like I only understand the basics. Just like with any other aspect of C++ or any other programming language or field of study, it takes practice and exposure to understand something. So, if you find yourself a little confused but wanting to know more, go check out resources on how to implement C++ template functions and template classes. It's a little uncomfortable at first, but eventually you'll get the hang of it. Okay, now that we have our callback function and callback component defined, we need a system that will allow us to use the component's function to modify other entity components. As you can see on line 1, we're again using template parameters with the same names, t and args. Starting on line 2, we define the callback system's update function, which is what gets called every game loop. It receives a reference to the ECS manager and receives string IDs corresponding to the callback system, the callback component, and the other components on which we intend to operate. Line 6 retrieves all the entities for which the callback system applies. In this case, somewhere else in the code, the ECS manager has kept track of the entities that have both a highlight and a callback component, so it returns this collection of entities. On line 7, we iterate over each of these entities. On lines 8 through 10, we fetch the entity's callback component, and on lines 11 through 13, we retrieve all the components on which the callback function needs to operate. Lastly, in line 14, we apply the callback component's function to the collection of required input components. And since we're dealing with a reference to the entity's components, changes to these components that are performed inside the callback function should directly apply elsewhere. Easy peasy, lemon squeezy. Except not. This took me weeks, maybe months to figure out, and this isn't even showing the hardest part. The getEntityComponents function on line 12 was a nightmare because I was previously unfamiliar with C++ parameter packs, and it took forever to understand how to pass an arbitrary number of types. Furthermore, just as I was writing the original draft of the last few sentences I've just spoken, sometime back in October or November of 2023, I encountered a very nasty bug. It was so bad that I dreaded and pushed off development for weeks and months, fearing I'd never be able to resolve the bug and that I was a phony. At last, something clicked into place in the second or third week of January, and I was able to resolve it. Of course, shortly after, I found yet another related bug that fortunately only took a couple days to resolve. Suffice it to say that I'm incredibly happy to be done with this feature, at least for now, and I'm confident each and every last bug has been eliminated from the Tartarus engine. So now, when we combine all this new functionality, we're able to implement component-component interactions via the callback component and have auto-generated callback systems manage those interactions. Here's a demo of the exact callback function we've been describing. When I click the square and cube, they're simply highlighted via their axis-aligned bounding boxes. See Engine Devlog 3 if you want to learn more. I never gave these two entities callback components, so nothing new or interesting happens. However, when I click the triangle, which does have the appropriate callback component, it turns to some pre-specified solid color, which I just happen to set to light blue. I haven't yet implemented a system or callback function to switch it back to its original color, so nothing happens when I unselect it, but that's very simple to implement in principle. Here's another wacky example. I've given the timestamp entity in the top right a callback component whose function will begin executing at the 30-second mark. The callback function operates on the entity's text and transform components and does all kinds of crazy stuff. It changes the text to show the entity's position, moves the text leftward and downward, ramps the text Y scale toward increasingly negative values, and slowly changes the color from white to red. And remember, I didn't have to explicitly define any new systems to perform these operations. Rather, I just needed to instantiate a templated callback system, define an interaction function that's passed to a templated callback component, and attach the component to the entity. Here's the actual code of that callback function, doing everything I just described. The callback system and component dramatically simplify interactions between an entity's components, and I think we're getting outrageously close to implementing buttons. I'm stoked. Thanks for watching. If you enjoyed this content, I'd appreciate a like and your subscription if you want to stay up to date on this devlog series. As usual, please feel welcome to leave your ideas and suggestions on what features or content you'd like to see in a future devlog video. Until next time, remember that reconciliation is one of the greatest experiences known to mankind, and it's far more fulfilling than the pride that comes with being right.